There are several properties of logarithms that are important to get used to as you go back and forth between logarithms and exponentials. And I have them listed over here on the right. And let's start with the big one. When you see something like this, okay, which just says the logarithm base b of a equals c, the way we interpret that is by thinking about what that means in terms of an exponential. What it means is b raised to the power of c equals a. This is always the way I break these things apart. Now, to write that as an equation, it looks like this: b to the power of c equals a. So that makes a few of these other things follow pretty simply. B to what power, for example, if I'm looking at this next one now, b to what power equals 1? Well, that's always going to be 0. B to the 0th power equals 1, which means if you ever take the logarithm of 1, the result is always 0. It has to be. So we can answer one of these questions very simply, right? Anytime you see log of 1, the result is always 0, because 0 is the exponent required for some base raised to that power to be equal to 1. Now this next one right here, that can be a little challenging to explain, at least algebraically. And what I'm going to do is fall back on this idea that exponents and logarithms are inverses. So without getting too much into the messy details, when you have two functions that are inverses and you take an exponent and raise it to a logarithm, you're essentially just canceling stuff out. So what I'm going to do, just knock those out, and all that's left over is a. Now, why is that useful? That's going to come up more in equations. But you can see right over here in this problem, if I have 9 raised to the log base 9 of 7, all that's left over when I cancel those out is 7. Now, these other two problems, these are more typical that you're going to see with logarithms. So let's work through those with two examples. Okay, I do not know why that ruler just appeared there. That's just great. Okay, so if I take log base 5 of 1 over 25, what I can do to simplify this a little bit is just rewrite that and say, okay, log base 5 of 5 to the negative 2. Okay, what does that equal? And I'm just going to put something over here on this other side and say, let's call this c. And now I'm going to change this into an exponential. I'm going to say 5 raised to the c equals this argument. And you'll see when I rewrite this, it becomes a whole lot more clear what I need to do. 5 to the c equals 5 to the negative 2. Well, c has to be equal to negative 2, right? It's the only exponent that's going to make this equation true. So the answer is negative 2. You can imagine that's kind of like canceling out both sides, if you want to think about it that way, right? You could cancel out the 5s. It actually works. I'd be a little cautious about that because sometimes canceling out doesn't work. But in this case, when you have a single exponential on each side, you're fine doing that. And then this last one, I'll say log base 4 of 64 equals something. Well, I don't know what that something is. We're trying to figure that out. Okay, so let's say we're going to rewrite this and say log base 4 of 64, if you remember your tables, is 4 to the 3rd power. And if you ever see a problem that says, here's a hint, without a calculator, that means you should be expected to be able to either figure these out in your head or just guess a few exponents until you find the right one. There's never going to be any ugly decimals to deal with when it says use it without a calculator. So this is equal to c. And now if I raise this power over here and rewrite it as an exponential, I see it says 4 to the c equals 4 to the 3. And you can see just by looking at it that whatever c is, it must be 3 for this equation to balance.